Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Last time we started to talk about heuristic function. The heuristic function estimates the cost from the current state to the goal state. It doesn't have to be perfect, but it has to be as we closer to the actual cost as we can. As we will see inshallah in this lecture, it shouldn't be, or next lecture probably, it shouldn't be pessimistic. It can be optimistic. Last time we saw two examples, and we started the third. The first example was the pathing problem, where I want to go from this state to that state, and we mentioned two heuristic functions. The first one was the Manhattan distance, which is the distance in both dimensions, distance in x dimension plus distance in y dimension. And we also mentioned a Euclidean distance, which is the straight line distance between the current state and the goal state. And we mentioned that this one is maybe the Manhattan distance is a bit better because it gives a better estimation to the actual cost, since Pac-Man cannot go diagonally. It has to go either in x or y dimensions. Although it is now the Manhattan distance also is ignoring the walls, but that's okay. The second example that we studied last time was the traveling problem from Arad to Bucharest as usual, and we mentioned that we can use also the distance between the cities to estimate the cost going from one city to Bucharest. So that was the second example. The third example that we started to talk about last time but we didn't finish was pancake flipping problem, where we have 4 pancakes. They are different in sizes, and we want to eventually order them by size, so that the smallest one would be at the top and the largest one will be at the bottom. And what we can do to reach that goal is to flip the pancakes at some position. So if we use the handle to flip at that position, then we will reach that state, because it will flip the top pancakes. Okay, if we do it at the third, let me change this. If we do it at the third position, we get into that, and if we do it at after or below the largest one here, we'll get to that state. We mentioned that the cost will be the number of pancakes that we flip in each step. So given that we have something like this state space graph between the states, what could be a heuristic function? What could be a good heuristic function in this case? Any suggestions, Saad? Number of pancakes that are out of place can be a heuristic function. Why? Why that could be a good cost, Saad? Okay, and we have to flip that number of pancakes anyway. And if there are 3, for example, that are out of place, they are not in their correct position now, then at some point we have to flip these 3. So the cost will have to be more than 3 anyway. So that's the minimum cost that we need to reach to the goal. Okay, so that's a good heuristic function. The heuristic function, any other suggestions before I tell you what we will use actually? Any other suggestions? Okay, so let me tell you what we will use here is the number or ID of the largest pancake that is still out of place. So this is a bit different from what Saad said. Here we look at the state and we check what is the largest pancake that we have to flip, and the cost will be the ID of that pancake. Let's see what will that give us, and why that could be a heuristic function. So if we look at this this state, the largest one that is out of place is this one, okay, which has an ID of 4. If we order them 1, 2, 3, 4, so the ID of this pancake is 4. So the heuristic function will give us for this 4 as the estimated cost. Now, why 4 might be a good estimate is that we have to put this pancake into its place, which is 4, okay, which means that we have to flip at that position at some point, okay. Otherwise, we will not be able to reach to put that pancake into that position. Okay, so this is like how deep we have to go to flip the pancakes in order to get to the goal. Okay, of course, it will not give us the perfect cost, which we shouldn't target anyway, because if we know the perfect cost, we would have found the solution. But that's a good heuristic function. Let's see it on another example. Let's see it on this example. We'll see that the heuristic function here will give us a cost of 3 because the largest one that is out of place is this pancake, which has ID 3. So the cost here will be 3. Okay, and again, the justification is we have to do a flip here at some point in time, which will have a cost of 3. So we are sure that at least the cost will be 3. Okay, of course, at the goal, the cost will be 0. So this is another heuristic function besides the heuristic function also that Saad mentioned, which is the number of pancakes that are misplaced. Now we will study a new search strategy. All of what we studied so far in the previous lectures were uninformed search strategies, which don't consider the goal when we expand any node from the search tree. If you remember, we studied 4 strategies: DFS, BFS, iterative deepening, and uniform cost search. Today, inshallah, we'll discuss, I hope we'll have time to discuss 2 new strategies. The first one is called greedy search, and both are informed, which means that they consider how far we are from the cost in every step. So in greedy search, we expand the node that seems closest to the goal. So at any point in time, we have the fringe, we have the nodes in the fringe, we look for the node that has the least cost to the goal. Okay, which is kind of logical, right? If I am in a position and I want to take a direction to the goal, I should take probably the direction where I think it is the closest to the goal. Now the question is, how can I know which one is closest to the goal? Of course, by using the heuristic function. So we will have the heuristic function. The heuristic function will give us an estimation of how far the goal is from the current state. And based on this estimation, we will expand the next node. Okay, we call this estimation, by the way, forward cost. Okay, forward cost, of course, we will have backward cost also at some point, but for greedy search, we only look at forward cost, and it's forward because it's forward in time. In terms of the time, it will be the future for us. So estimation of our future steps, what will be the cost of them in order to reach to the goal. So we'll do that on the traveling example. We start from Arad. The estimated cost of Arad is 366 to Bucharest, but of course we don't have other options other than expanding that node in the beginning. Now we expanded, of course, with the 3 neighboring nodes or cities. Now we look at the estimated cost from each of these cities to Bucharest. Okay, how can we know that? From the heuristic function. Okay, so the heuristic function will give us that estimation. So based on the heuristic values, we get CBU to, or CBU, I don't know how it's exactly pronounced. It's 253, so it's the least cost, the one with the least cost to the goal. So this is the one that we will get out of the fringe and expand it to its 4 neighboring states. Now we look at which of them is closest to the goal. The heuristic function tells us that it is Faragas, so we will expand it next. Now Faragas will be expanded to these two nodes. Now at that point we have 1, 2, 3, 4, 5, 6, 7 nodes or 7 states in the fringe. The one that has the least cost, of course, is Bucharest, since it is the goal. So the estimated goal to Bucharest from Bucharest, of course, is 0. So we will expand it, or we select it, and then we declare success that we found a solution. Okay, so this is the greedy search strategy. It's greedy because it only looks at what could happen in the future. Okay, so it will try to find, or it actually expands the node that has the least cost in the future, going from that node to the goal. Okay, now the question is, what can go wrong here? What is the problem with this strategy? Any idea? Okay, Saad? Okay. Okay, so you mean that sometimes it might take decisions that are not globally optimal, they are not the correct decisions. It's not considering the total cost of the path. Okay, it only looks at the future. Okay, so that's exactly what can go wrong here. So as you see in the cartoon here, you might think that this path is good, but eventually you will find that it will not bring you to the goal, and you have to maneuver and go back into another direction. Okay, that's the nature of any greedy algorithm. It takes local decisions, decisions that are not informed with the entire environment. So it might sometimes it might make good decisions, but in other times it might make bad decisions, and bad decisions will divert us from the goal, going far from it, and then we'll have to come back. So the strategy again is to expand the node that you think is closest. The heuristic will give us the estimation. A common case, which is the best first, might take us straight to the goal. It can happen that it will take us straight to the goal, but in some cases also the worst case might happen, and we'll have to go a long way around the goal before we turn back and reach it. Here is a demo that will show you sometimes the greedy search will be really good, and sometimes of course it will be bad. In this case we have just an empty world. We need just to go from this point to that point. The heuristic here is Manhattan distance. Okay, so here is how the greedy search will work. Sorry. Okay, so you see it got us to the optimal solution, okay, straight right away. Why is that? Because the Manhattan distance here is actually very accurate. Okay, it's actually perfect because nothing is here in the world, so the actual cost is exactly Manhattan distance. So the greedy search was able to make globally correct decisions, and it reached the solution in an optimal way. Here's another example with the maze. Let me first explain what will happen here. Here we have a maze, of course, with walls, and we need to go from this position to that position. And what you will see now is a pattern of going through the states by Pac-Man. When you see the block that is darker, that means that Pac-Man went through that state more than one time. So as you go over the state more than one time, it gets darker, and it will be light if you just went through that state just once. Okay, so let's see how Pac-Man will solve this problem here using greedy search. So what happens here? You see that this is darker, of course, this area is darker than this area, okay? Which means that Pac-Man went through this path first, it seems, okay? And of course, we found that it's blocked here, and it went back and went through this path. Okay, of course, this is clearly not optimal. Okay, for example, here, the optimal solution for Pac-Man here was to go this direction, okay, to go to the right and going through this direction. That would have been the optimal solution, but the greedy search algorithm, which is using here again the Manhattan distance, is not giving us the optimal solution. Any justification why Pac-Man went through this direction, not to this direction in the beginning? Ghanem? Exactly. Yes. So yeah. So at the beginning, okay, Pac-Man had three possible directions, right? Right, left, and up. But it went through the left one. Why is that, Ghanem? Yes, because this point is the shortest according to the heuristic Manhattan distance to the goal. Okay, so it was the best for Pac-Man to make at that point, and also that happened through this path. Okay, going through this path, that was the only solution, and it had to go this way and then come back through that way. Of course, it took long time until it reached a solution. Okay, thanks, Ghanem. Now let's move on to another algorithm. Now, if you look at what we studied so far, the best algorithm that used to find an optimal solution was uniform cost search. But it was really slow because it looks at so many directions before it gets to the optimal solution. On the other hand, we have the greedy search algorithm, which looks fast in making decisions and going some times going to the right direction, although it sometimes in other times it doesn't. If you remember the story of the race between the turtle and the rabbit, the turtle is slow but steady. The rabbit is fast, but sometimes he is lazy. He wants to have fun through the race. So he slept, and eventually the turtle, although she was very slow, it was able to reach the finishing line before the rabbit. So you can think of the turtle as uniform cost search, slow, but it will reach eventually the goal. The rabbit is a greedy one, and we would like both together. We would like something that will have the goodness of both together, which will be the estar algorithm, which inshallah we will study next. Okay, any question before we get into estar? Okay, so what is estar? Before we get into estar, let's see on this exact algorithm, in this exact example, how uniform cost search and greedy search will behave. Okay, so let me, I need help from you now. So someone please volunteer and let's go through this example using uniform cost search first. And on the right you would see the search tree already. So that's the whole search tree, or at least big part of it. That's for illustration, but we'll have to expand it incrementally for every algorithm. So anyone for uniform cost search? Hamza? Hamza, I don't hear you. Okay. Okay, it is the left one, and the right one is the search tree. So how can we start with this? So we will have to go from the start state to the goal state. So what should we start with? Okay, so in the beginning, we should start with the S state, of course, right? And then A, okay. We don't have any other choice. Okay, first we need to expand A to B, D, and E, right? So we have 3 of them. Yes, we'll have the 3 of them. And the cheapest one is B. Why is that? B has the cost of 1. So what is the cost that we are what is the cost that we are looking for here? The past, right? Which is G here. Okay? So the cost of B is 2, not 1. Okay? So uniform cost search only look at the G values, which is the backward cost, right? So here G is 2, here G is 4, here G is 9. So we'll take B. And we expand B to C, right? Okay, now we have C, D, and E. Which one we should expand next? Yes, which one we should expand now? Why is D? But here G is 3, right? No, we didn't expand it yet. Still, C and D and E are in the fringe. Okay, we didn't cross them yet. Yeah, but we don't know in advance, Hamza. Okay, so we'll have to expand it. Okay, and we found that there's no children, but at least we get it out of the fringe. Now we have D and E. But at that point, what did we do actually? If you look at, if you think about the problem, we went through S to A to D to C, right? Which is completely wrong direction from the goal. And that's because uniform cost search, of course, doesn't look into the goal. Okay, next, you will expand D or E? D, okay? So we'll expand D to G. Now we have G. Okay, now 6 and 9, which one should be expanded next? G, and we expand G, and that's the solution already. So that means that we found the solution, which is, of course, this is the wrong path, but we found the solution, which is SADG. Okay, and this is the optimal solution, but we found it after we went to the wrong direction, which is SABC, and then we came back to find the optimal solution. Thanks, Hamza. Okay, for the next one, we need to check the greedy search. What the greedy search will do in this case. Any volunteer? The other Hamza? Okay. So one by one, Hamza. Okay. SA. So SA. So what do you look at, Hamza? The H or G? H, because that's the forward cost. That's the heuristic function. Yes. So we'll expand A, of course, to B, D, E. Okay. And which one will be expanded next? E. Why? Yeah, H is 1. So we think that it is the closest to the goal. So we expand E to D. Now we have D twice and B. Which one we should expand? Actually, you need to arbitrarily choose one of them. So let's take this one. So D will be expanded to G. Now we have G and D. Okay, of course the heuristic here is 0, and the heuristic here is 2. Okay, so should we declare success now? We get G out of the fringe. Yes, so if we do that, then that means that we found the optimal solution. But as you see, we started with SAE, okay, and that's not the, sorry, that's not the optimal solution. We actually, what we got here is SAEDG, okay, which is not the optimal solution. Okay, so the greedy algorithm, of course, sometimes will not get us to the optimal solution. Abdurrahman, thanks, Hamza. Abdurrahman, do you have a question? Yes. Yes, generally, of course. No, 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 no. Sorry, Abdurrahman. The greedy doesn't look at the cost in the past. It looks at the cost forward in the future, which is given to us by the heuristic function. Yes, as we assume always the heuristic function, of course, should not be that complex. Otherwise, it will be slow. So yes, yes, we assume that this is you can say that this is a design feature or a design requirement that when we design a heuristic function for any problem, it should be fast. It should return the estimation fast. It doesn't take a lot of time, so it shouldn't be complex function. Otherwise, as you said, other methods might be faster. So we assume that the heuristic function is fast. Here, the heuristic function. I don't know whether this is of course a toy example. It doesn't tell us exactly what the real problem is. But in the traveling problem, for example, it's just a lookup table. Okay, we don't need really to go and measure the distance. It's a lookup table from the knowing the distance between cities, so it will just be very fast. Okay, again, also Manhattan distance, for example, is very fast to compute. So this assumption is not bad. It is an assumption, yes, but it's not bad in many cases. Did I answer your question, Abdurrahman? Okay. Okay, now let's see how the A star search will work in this case. Okay, sorry. Oops. Okay, do you still see the... I think you don't see now. Okay, let me share again. Okay, I think you see it now. Okay, now let's do A star. So what A star will do is to get out of the fringe the node that has the least total cost, least estimated total cost, which is the backward cost, which is the cost from the start state to the current state, plus the estimated cost from the current state to the goal state. Okay, so it will add both values, backward and forward, g of n plus h of n, which is, we call it here f of n. That's the function that we will use to expand the one node from the fringe. Of course, we will pick the node that has the least total cost. Okay, the node that has the least total cost will be expanded next. Now, I will ask for a third volunteer to do A star with me on this example. Anyone? Saad? Let me... Yeah, let's do it one by one step at a time. So we'll start with S, right? What is the cost for S? Which is 6, yes. Okay, so the cost for S is 6. Okay, now we expand to A. Now, which is again 6. Okay, okay. Then we have no other choice other than expanding to B, D, and E. right? Now, what is the cost for each? B. Why is it 8? Yeah, so the backward cost is 2, okay, and the forward cost is 6. Now, why is it the backward cost is 2? Yeah, if you look at, yes, all the way back from the start state to the current state. So SAB is 1 plus 1, which is 2. What is the cost for D? Okay, which is 6. And here the cost is 10. So which one we will select now? is D. Okay, so we'll take, we'll expand D next. We'll get G. Okay, what is the cost of this G? Which is 6. Okay, now we have 6, 8, 10. So, yeah, so we'll take this, which is now the solution that we found, which is actually the optimal solution in this case. Okay, so we found S, A, D, and G. So this is A star, and as you see, A star combines both uniform cost search by considering the backward cost and the greedy search by considering the forward cost. Abdurrahman? To be to نوت يعني ايه بالظبط؟ ما خدش بالي. Okay, it's not two things. Addition, of course, is not that slow, but here the cost, the time is in terms of the states that we expand, Abdurrahman. Of course, the computation will take time, but the computation here is very simple. It's just addition. So the number of states that we expand is much more costly. So the A star algorithm here will get a better solution than the greedy algorithm because it takes into consideration the backward cost and the forward cost, and so it will be a bit better in terms of the solution that we will found in most cases, and it will be faster than uniform cost search because uniform cost search is blind in terms of where the goal is. So it expands into many directions that might be found eventually to be wrong. Okay, so it tries to be as good as uniform cost search in terms of finding the optimal solution or a good solution, and as fast as greedy algorithm. Okay, it might not be faster than the greedy algorithm, by the way. Okay, but it tries to be somewhere in between to get a fast enough algorithm and optimal or good solution. Okay, we'll see how. Not all cases, very good. Yes, not all cases. Yes. Okay. Now, when should A star terminate? Should we terminate when we found a goal, when we enqueue a goal into the fringe, or not? I think we answered this question for the previous strategies, and we said that we should not, of course, stop when we enqueue a goal. Enqueue means adding the goal to the fringe here. We should stop when we get the goal out of the fringe. Let's see what will happen here in this example. Let me ask for a volunteer here again to do this example with me. Anyone? Ghanem? So we want to, yes. So we'll start with S, right? Yes. So we have to expand S first, right? So we'll have to expand to S to A and B, right? So what will be the cost for A? The cost for A is 2. No. The cost, we are doing A star here, Ghanem, right? So the cost is the backward cost plus the forward cost. For what? For which node, Ghanem? A or B? For A. Okay. The backward cost for A is what? No. Okay. So backward is from the start state. So the cost from the start state to that state is what? To A is what? Yes. So it will be 2 plus the estimated cost from A to G, which is, because we have H here is 2, right? So H here is 2 plus this 2. Okay. So the cost for A will be 4. How about B? How about the cost of B? No, backward is 2. Yes. No. The forward is the estimated cost, because we didn't expand this node yet. We don't know what exactly will be the cost, but we have the estimation, which is the H value, the heuristic value. Okay, so the total cost will be 3. 2 plus 1, 3. Now, which one will be expanded next? B. Okay, so we expand B to, B will give us G, and what will be the cost of G? No. Backward is from the start state, Ghanem. Yes. Okay, so 3 plus 2, which is 5, plus the forward cost is, no, the forward cost is 0, because the H here is 0, right? Yeah, so the backward is 5, forward is 0, so the total will be 5. Okay, now if we stopped here, we should not stop here, right? Because actually this one is 4. Okay, so we might find a better solution here. So what we'll expand next is A. So we should not stop here. We should expand A to G. But this G now is different, right? What is the cost in terms of the cost? Might be different in terms of the cost. What is the cost of this G, Ghanem? Yes, and forward? Yes, so the total will be 4. Okay, now we have these 2 G's. Which one should be taken next? The one with 4, yes. So now we got this path, okay, S to A to G, instead of S to B to G. Okay, so the answer to this question is no. We only stop when we dequeue a goal. Okay, now is A star optimal? Thanks, Ghanem. Is A star optimal? Inshallah, we'll answer this next time. So we'll have to stop here. Inshallah, we'll talk to you on Tuesday. Assalamu alaikum wa rahmatullahi wa barakatuh.